Well, hi everyone, and thank you, Lorenzo, for having me here today. I work at Google Deepmind, so most of the work that I'm going to be talking about is the work that we've been doing as a big team at Google Deepmind. We care a lot about manipulation, so it's also going to be centered on manipulation. I'm not going to be talking too much about tactile today, because I think you already had a lot of speakers talking about it, but I'm definitely going to be covering how we think about robot learning and maybe some insights that might be useful for you if you want to pursue some more work on robotics. Let me see if this works. Okay. Just some motivation. I think robotics is a grand challenge. And I think it's grand because it can really help us. It can be disruptive and bounded. It can affect many things. If you imagine robotics working, I think the implications are vast. But I think it's also a challenge. And I wanted to go in more into this because you need to satisfy lots of constraints when you think about robotics. And I think that it's something that we don't always think about it. Definitely if you go to some general audience, they have never thought about it, but you really need to think about this curse of the 99.999% success if you really want a robotic system that can be deployed into your environments. So I like to put an example, which is imagine you have to have a robot just pick a mug, like the simplest example that we always put, right? And now let's say you have 10 mugs at home and it breaks one every, let's say, 10 days. Then what's going to happen to your mugs? Well, you're out of mugs very soon, which is not great, but maybe your robot is a bit better, and it only breaks a mug every 100 days. Doesn't seem too bad, right? But actually, every 33 years, you're out of mugs, which probably has never happened to you, that you have to change mugs every 3 years. But you have lots of things in your house, so you can clearly see how this 99.9, which is what you will get from here, is actually not happy. So you really need very good precision, but also generality, because this needs to go into your house, but probably this system needs to go into everyone else's house. So how do we think about it? I think this is why I would like to say that robotics is really a challenge, and we need to think about it. So when we think about this problem of robotics in Google, we want a system that can be both precise, capable, and safety, as much as possible. We cannot just cut corners. We really need to have all these aspects covered. And now, you might know that at Google, we have Gemini. Gemini is like ChatGPT, Claude. It's our version, it's our large language model. And now we combine it with robotics. And this is the second version that we released, which is the 1.5 version. And the idea is I want to have a model that can really reason and be very capable, but that it sits on the knowledge that we have from these large language models, this Gemini big model. You can imagine this is not one or two people, this is a large team, but actually comes to talk about the multidisciplinarity. Lots of people need to come to make these systems possible, from software engineers, researchers, electricians, so lots of people actually just to make this possible. So I want to acknowledge that. So let's go into what we want to do. I think you might have heard, maybe you know about Demis Hassabis, there is the idea of AGI, right? This artificial general intelligence. For us in robotics, what we want is to be able to create an intelligent, capable, and helpful robots again. And I think there is a few axes that you want to think when you think about robotics, right? In our previous release, which you don't have to know about, we touched a lot on interactivity, dexterity, and generality. Well, we were able to do things like those. You have some teleoperation system, you teleoperate, you collect several thousands for this task, but then you can actually get origami to work. So now you have one model that has been trained to do origami with lots of teleoperation. And you go from this kind of a square paper into something that is going to look like the face of a fox. This is good because you show that even without tactile, there is no tactile sensing here, you can get these robots to perform a task that is long horizon, but also very dexterous. But then again, this was trained, so it only knows how to do this task, and it required a lot of data. So this is good, but it's clearly not this one system that can do everything that we need it to. So now the word that I'm going to present is the 1.5. As you can imagine, a 2.0 is coming, and probably more. But what we expand is on, can we also be agentic, which means now the agent can also think and decide what to do. Sorry, I cannot read what I put there. Okay, the thinking part. And then that's the other very important part, is that this one model we just control one robot, or it should be able to control several robots. Now you might want to think about the Android of robotics, right? So within there is value in not just finding a solution that works from one robot, but forcing our models to be able to control multiple robots with different joints and degrees of freedoms, with different embodiments. And again, with one single checkpoint, with one single model that can do all of this. So I'm going to touch across some of these things, but again, I would say the most difficult embodiment that we have right now is a humanoid. Humanoids are actually pretty difficult because anyone wants to guess how many degrees of freedom this guy has?
55?
No, it's a bit less actually. It's 32, but we're actually going into 55 or more soon. But 32, it's not as small. Then you also want to think about, usually most of the world that you see is planar. You have your table and you just do the things in the 2D world. This seems a stupid thing, but when you try to collect data that goes more into the 3D world, if you think about dimensionality, all the reasoning actually scales quite a bit. So that became a bigger challenge than what we thought. And finally, we also care about dexterity. Dexterity, if you don't have it, you are not really solving manipulations. So can we push on the axis of how many dexterous tasks we can actually solve? So let's just start with the idea that we want a system that is as general as possible. You can go into the report, there is all these numbers, but this is just to show that the more data and the more quality that you can put into your data collection, I'm not going to talk about this, but collecting data ends up being one of the most important parts of your robotic systems. If your data is not so good, that's not going to turn into a very good model. And that's actually true even for LLMs, right? You really want to have very good data. But once you actually go and do that exercise, what you find is that actually, because you're also sitting on top of this Gemini, this large language model, you can really solve the same task even if you have different instructions, even if you have different objects, different visuals, clutter, and even if you have a combination of all those things. So we were able to go to a robotics conference, put our system, that was actually in Korea, so we had to move it from London and US to Korea, and then people was going there and asking questions. We would give them a microphone and they would say, can you put this on top of that? Can you open this thing and then maybe cover it, and it was able to do it, right? So that's what comes when you actually are able to collect lots of data and do things at a scale. The other thing that for us was very important is we want to have a model that can do more than just controlling one robot. And this is just, again, numbers that show that, yes, the model can do it. I'm not going to go into the details. What was very important for us is if you have to collect the same task for 3 different robots, that's not a scaling, right? The scaling is very important. So ideally, what you would like is that if I collect this task on this robot, can my other robots already learn how to do it? Ideally, even if the task was collected on a bi-arm with grippers, and I actually want my humanoid to be able to do it. So this kind of cross-embodiment, it's something that it's easy to neglect and say, I'm just going to do everything from this robot, and then the robot is going to be very, very capable. But for the purpose of Google Deepmind, it's very important that we have this cross-embodiment, that we just don't tailor to one solution, but actually our model can learn the task in a more kind of abstract way so that different robots can still do it. I'm not going to go into the details because unfortunately not everything that we do we publish, which I think is something to remind. Industry is not academia. You now have the luxury to be in academia, so you have the luxury to actually learn, explore, present, publish. We don't explain everything we do, but here you have a sense of what I mean by transferring. So we collected data with this robot. This robot is now taking this paper, and it's meant to, don't ask me why, clean this pier, this big pier. And it does this behavior where it grabs the cloth, and then it just went and removed some invisible dirt from it. And I guess the point is that then we ask the same instruction into the humanoid. And again, you need to think about it. Like, this is 16 degrees of freedom. This is 35. This one has hands. This one has grippers. The way you grab the cloth is not the same. Positioning is also different, and still is able to do some of the behavior. Is it perfect? No. This is not a final solution. It's very far from the 99.9, but this came for free in a way, right? By using some techniques. I think that's the value that we want to cover here. And then something that it's important to remind is that you're collecting data But the data is just being collected, right? There is no instruction that really is the instruction, right? There is many ways in which you can describe anything, like picking, grasping, moving, putting. Semantics is a nice problem, and with LLMs, it's pretty well understood. But I think when you think about robotics, there is something about what should I be doing next? And if you just say, okay, I want you to do this thing, that might be too descriptive and might not be sufficient. So what we do here is basically allow the robot to kind of tell itself what would be the next thing to do. You say, I want you to clean the pier. Well, then the robot will be like, okay, first I need to grasp the cloth, and I need to do this, and I need to do this. The robot itself is able to kind of think and decompose a task in subtasks that is confident that it will be able to achieve. And this is, again, just showing that if you do this thinking, and if you let the model think while it's acting, that actually helps performance. So this is Gemini Robotics, and I think right now for us is the most powerful model that we have. But I think if you pay attention to the details, I have mentioned a few things several times. One of them is that we do teleoperation to collect all the data. I'm not sure, has anyone ever here teleoperated a robot? How did it felt? Okay? Amazing? Was it doing exactly what you wanted it to do? Usually not, right? Usually it's like you kind of do it, and the more you do it, I'm very bad at it. But usually the more you do it, the better it does. But it still doesn't feel human, and clearly it doesn't feel superhuman, right? It just feels like, okay, it's managing. It's better than nothing. And I think that's the problem that we have here. Lots of the data that we collect right now, because it's easy to scale, you just need robots and people and a system that does teleoperation. Once you know how to do one, you can do 1,000 of those, you can do 100. But the problem with this is that it's really a bottleneck. Your model is as good as your teleoperation data, and as we were saying, even if you try really hard, it's not amazing. And it's also very expensive. As I said, the recipe you can scale, but it's not a cheap one. You need a person, you need a robot, and you need a teleoperation device, and you know every time you want more, you need to buy more of these cells, hire more people, and keep on going. So this is not a solution that scales. Yes, please?
I'm just curious to know more about, like, have been tried, like, Gemini is really good at generating videos, like,
yeah.
is great at it. Or do you think the quality of that, like, kind of AI-generated footage is really bad?
We have definitely tried. The way I think about it is, when we tried maybe a year ago, even the gripper, would kind of, after a few frames of prediction, it would kind of degrade and kind of blur. Contexts were terrible, but that was a year ago, and as you know, these models are improving a lot, so what we have right now is much more promising. So I would say this is an active line of research. It's not yet something that we have, and especially as you do things that are very complex, or if you go into occlusions, that might become a problem, but I think it might become at some point, if good enough, like a word model that you can plan and reason over. It might be able to give you data, but it may also help the robot to say, okay, if I do this, does that make sense?
I was also wondering, like, can you use unrelated footage for training of that? Like, for example, obviously there's so many videos of just people doing stuff on YouTube, and I know, like, this is also like a very active area, so I'm just curious if you explored that.
Thanks a lot for the question. That's a great question. And I want to say, if anyone else has a question in the middle of the talk, please jump in anytime. I think that's going to be funnier for me, or nicer for me, and probably helpful for you guys. So coming back to your question, I think I said already that data is very important, and data quality. So you could, and that would be amazing, right? But that would be like, if you think about these LLMs, they have two phases, or even three, right? They have the pre-training, put all the internet, see what happens. You post-train, and then you even do RL on top from human feedback. So I would say for us, probably YouTube will be like pre-training. This is not the best data, but there is so much of it that there is value. But then I think there's still going to be room for saying, okay, no, this is very good data. And now the question is, this very good data, is teleoperation good enough? And maybe at some point we're going to find a way in which we record the data from humans that is really good. But I think right now what you have in YouTube probably is not good enough, because none of the videos is like looking at the hands doing something, right? Most of these are on the scenes, things happening. So there is value, and I think it's going to happen. But I still feel, at least for a while, we will need very high quality data. Yes, please?
I had a follow-up, like,
about data. How about data like from simulation, or is it just not good enough?
This is a very good question. I'm gonna touch on some of this. For those of you who don't know, Google DeepMind owns Mujoko. We support Mujoko. That one is open source. We really want everyone to use it because we think there is lots of value in data. Simulation data can be very helpful. It's not in this release, but it's something that we actively work on because the beautiness of simulation is that it's very scalable. You don't need a robot. You don't need a human. All you need is a computer. And if you can make the operation of some device easier, you could imagine someone at home kind of doing a video game and giving you lots of data. So I think simulation is very attractive. The problem with simulation is that when you go into things that are articulated, deformable, that they can break, then it becomes hard to simulate. And then you have this kind of trade-off, or I would like to simulate this, but it's going to take so long that it's not feasible. Or the effort that an engineer needs to put to make these objects simulatable, it's so high that I would rather just go and do teleoperation. So we always have to balance these kind of questions. So I want to motivate the word I'm going to talk with this example, which is if you were to open some earbuds. Because usually if you were to do it yourself, you would do something like this, very natural. But if you were to teleoperate, you would do it like that, where you show it into the camera, you are very careful, you do it always in the same way. So not the most natural, but you know this is going to work if you do teleoperation. And then there is maybe, I'm calling it the best way, but it's just like maybe the superhuman, the way that is not the way we would do it usually. And the question is, how do we get data, right? Yeah?
Has there been any attempt to use motion capture instead?
Motion capture for the human body or for the hands?
And then motion capture on the hands and maybe eye sensors as well on specific robotics?
So right now, lots of the, let me know if I don't answer your question, but a lot of the data that is collected for hands, you usually put a glove on. Because, I mean, some people will use the VR set, and then you put the gloves on, and that's usually the way you collect data. Because the gloves are on your hand, so I think the tracking error then becomes smaller. And because, again, we care a lot about quality, why risking it? What if my cameras or my motion tracker doesn't see the hand when I'm doing something, right? Well, the glove will always be able to tell where the finger positions are. So I would say for hands, usually you go with gloves on the humans, but you could also do tracking. I think for whole body, when it's locomotion and you want some, then is when you do a lot of the motion tracking. I would say that if you think about this problem, this would be the modular solution that we have done in classical robotics that I think has a lot of value, where you just decompose and you do something with control, maybe some perception. This is what immersion learning looks like. And I'm going now into reinforcement learning, because I think reinforcement learning might be able to go beyond suboptimal data and give you something that really is fast, reactive. And for that, I'm going to just talk about some work that we published in 2015, and then some extra work that is called ExoStart that kind of tackles about this problem of we want to go beyond teleoperation, how can we get data? And the goal here is that we want something that is simple and scalable. I've been talking about this all the time. That gives us nice behaviors that go beyond teleoperation. And ideally, no, not ideally actually, it needs to work on real robots. That's very important. None of our work, even if it's using simulation, can stay in simulation. They always needs to work in the real robot. And this is the system that we can map. It's going to open the earbuds. And you can see that the way it does it is not at all the way you would teleoperate it. It uses this side of the finger to actually do it. So it's very much non-human way, but this turned out to be extremely reliable for the robot to open the earbuds. So again, this is because this is reinforcement learning. You put, in our case, it's going to be a sparse reward, and from there it figures out the behavior. Yes, please?
When you're starting with simulation, how do you know when you're ready to make the jump from simulation to real?
Never.
Never?
That's a great question, though. That's what we call the sim to real gap. You probably have heard about it, and you try and see. The good news for us, at least, is that at some point we had one task working really well, and then the next 10 happen much, much quicker. So I think there is kind of a binary situation where things are working but not so great. You keep on turning things, And at some point, many tasks start working. Because kind of you solve the system identification, for instance. You solve the visual gap that you have between simulation and real. You solve a few things, and then that helps a lot. But there's never a moment where you can say, okay, now I know everything is solved. And probably if we would have pushed into more and more complex tasks for this work, we will have seen that, well, now this breaks again because my simulation is not good enough. So it's something that you need to keep on working, but once you have made progress, it pays off. And that's something that's important to remember. Thank you. So this is a bit how it goes. I'm going to go into the stages. But first of all, I also wanted to give you the motivation of how do we see RL. Reinforcement learning, if you just do it, it can go in any direction, but then you have to face the exploration problem. How do I find data? How does the model find examples or states from which to learn from? The way we resolve this problem is by actually using demonstrations. And in our case, what we do is we build this exoskeleton. That it's an exoskeleton that you put on. Our robot has 3 fingers, so it only allows you to move 3 fingers. And then you collect a demonstration. And now I'm going to explain how, but we can actually, by seeding our reinforcement learning with its states coming from this demonstration, the model actually is able to learn a policy that works in real. I'm not going to go too much into the details of this, but basically it's sensorized, it's a kinematic double. So you get exactly the joints of the robot. Well, not exactly, but a very good match between the robot and the exoskeleton. It records everything we need, object poses. We use fiducials, which is not ideal, but we use those for the demonstration only. And then, because there is this match, we can bring the demonstration that we collect in real into simulation. This is just the rollout of the simulation. The problem is that if you look very closely, there is a dynamic mismatch. Sometimes the object penetrates. That's because even though we are tracking, and I think that goes back to the motion tracking, even if you track, there is always errors that make your data low quality. So what we do after this is we have Mujoko. So we just run MPC. In our case, we call it NJPC, doesn't matter, to actually refine a bit the actions so that now they are actually dynamically feasible. Now there is no penetrations and the actions are correct. And now is when we now have this demonstration. We can use one. We use usually between 1 and 10. We don't need more than that to initialize our reinforcement learning. So this is what we call DemoStart. This is the algorithm, the reinforcement learning, that is based on demonstrations. And the idea is that we wanted something that scales. I think I'm going to say the word scale lots of time, because otherwise it's not something that we really can rely on to make progress. And for that, we use sparse rewards. That just means that instead of saying, oh, you go first here and then you get 0.2, and then if you do that, you get 0.3, this is, did the task succeed, yes or not? If it succeeds, it's a 1. If it didn't succeed, it's a 0. Everything in between, it's going to be a 0 because it hadn't succeeded. For demonstrations, again, you need to put the glove and collect 1, maximum 10. Otherwise, it's not going to scale. So very few demonstrations. And as a result, as you can imagine, this is much cheaper and it scales much better than teleoperation. And it has a promise that because of RL, it can give you behaviors that are faster and better than teleoperation. This is an example that I just showed because I like it, which is that we had this demonstration that was extremely bad. Because it was with a space nav. With a space nav, you kind of open, close, and did this. This is a sped up. It was extremely slow. It took over a minute to collect it. But because then the RL is going to select the states, it can actually optimize it and get something that works in 4 seconds. So again, just to show the power of teleoperation versus RL when you go to the extreme of not very good teleoperation. So how does again, binary sparse reward just means everything is a 0 until you succeed. In this case, the task is inserting a connector. And now again, the question is, if you have a sparse rewards, how do you solve the exploration question? And that's going to be by using, in a way that I would say is clever, the demonstrations that you collected. So this is the idea that I want you to get from this method, which is there are states that we can call informative. So what does it mean that in a state? A state means the object is here, the robot is there, the environment looks like this. What does it mean that this state is informative? Well, what it means for us is that if I roll out a policy at that state, is it going to succeed all the time? If it's so, it's not informative because it's too easy. There is nothing to learn from that state. If the policy you do roll out from that state and it always fails, it's also not informative because you have no clue how to solve it. But actually, we found that there is a state where sometimes you succeed and sometimes you fail. These are the ones that we call informative, because here the policy sometimes knows how to do it, not always, so there is something to learn. There is kind of signal towards how to guide learning. So the way it works in practice is that we have lots of actors, they just keep on trying states. You can make this clever, of course, but basically they try states, they say, okay, this is too hard, let's not even think about learning from this one. This one state is too easy, let's not try to think about this one. This one is informative, so let's roll a lot. And let's send it to the replay buffer so that my RL algorithm, and this can be any RL algorithm that runs offline, can actually take these states and learn, okay, this action is good, this action is bad. And from there I keep on progressing. Of course, then you're going to go to the learner, you're going to improve your policy, and maybe this state will no longer be informative because you have updated your policy, and now you can learn from it. You know how to do it. So I'm going to skip some of this, but I just wanted to give you maybe another idea of how DemoStar works, which is that it builds an autocurriculum of states. And the idea is the following. Let's say you have this task, which is, we call this sort out. You just put something up and put a screwdriver inside. So when you do demo start, you do the RL on top, you create an autocurriculum by default. You don't write it down. And the idea here is that this is time within the demo. If you're at 100%, the demo is succeeded. If you're at 0, you're at the beginning of your demonstration. And this is policy updates, training steps. So at the beginning of your learning, you're only using as informative states the states that are very close to the end of the demonstration. So here the demonstration is, the state is already solved. So what I'm trying to say here is that at the beginning, the states that are informatives are the states that are almost solved. As training progresses, you go from easy to hard. And what are the states that are informative now are those that maybe in this case, so at the beginning, all you had to learn was drop the screwdriver. Now what you need to learn is to pick the screwdriver. So these are the type of states that you see here. And then maybe now you're seeing states where you're not even close to the screwdriver, you just need to actually first go and then grasp. So basically, as you keep on progressing the learning, what is informative evolves, and it goes from easy to hard. Yeah?
Does it matter when you introduce like the hard states after training?
Say that again?
Does it make a difference on the amount of results depending on when you introduce like the harder states?
Sorry, I'm struggling.
I said that does it matter? Like, does the timing of introducing the harder states matter like, towards the end?
That's a great question. So we don't introduce them. We don't script this curriculum. This curriculum happens naturally. So actors will be sampling states across the demonstration, right? And when they sample a state, let's say we're here, and they sample this state. Because this state is at the beginning, almost nothing has been solved, it's going to fail all the time. This policy cannot solve it. So the actors are going to find that the only states that they can find some successes are near here. Let's say we're here, then these ones. These ones, well, actually, all these ones are probably getting solved, and these ones are the ones that are informative, where the policy sometimes succeeds, sometimes fails. So you're actually looking at all the states, but only some of them are informative. And as training progresses, what it means informative actually also evolves. Yeah?
This idea of starting from hard initial states similar to paper Go Explore, to what's diagnosis wasn't cited in DemoStar.
I see.
I'm wondering what was the reason for that?
Can you tell me more about the paper?
Yes, so Go Explore's whole idea was that you perform auto-curriculum learning by finding the states very much like this, which are almost solved. Like hard states, that's the whole thing.
Yeah.
To solve the exploration problem in RL. So it sounds similar.
It sounds very similar. If we didn't cite it, I would really appreciate if you want to send me the citation. We are very happy. Like, I think you now know that there's lots of papers. I'm sure that we missed some of them. We actually paid a lot of attention to try to include all of them. So I would be very keen to read this paper, and if needed, we can always revise and add it as a citation. Because, yeah, that could be. I mean, the idea of autocurriculum is not new. I think for the paper itself, it was the idea that this autocurriculum gives us policies that then we can actually successfully do sim-to-real transfer with hands. But please, send it forward. Let's just go into how it works. We collected some demonstrations, and then you put it through the pipeline, and here you can see how it learns to unscrew this object. Yes. And now you can also do the sim to real. I'm not talking a lot about the sim to real part, but this is actually one of the most important ones, making sure that sim and real align. But then you can see that the motions transfer. I'm almost done here, but basically I just wanted to show some of the in-hand manipulations that we were able to show with this project. This is cube orientation, that was inserting a key into a log. And this is the my favorite one, because you clearly see the in-hand orientation to get this in. And I think someone was mentioning this, we are using simulation to learn these behaviors, but the initial demonstrations for this work come from just collecting one or two with an exoskeleton. Just a few more. So the main idea here is that teleoperation is very good, it's limiting. Can we find solutions to go beyond that? RL is very promising. Of course, this is just an initial work. It needs to be scaled, it needs to be proven that the sim to real gap is something that we can keep on working. But I think it gives us hopes that there's definitely a path towards more than just teleoperation in terms of the behaviors that we can achieve. So with that, I wanted to acknowledge that a lot is happening. Both in GDM, I talk about some of the works, but I think actually also in academia, in other industry labs. I think robotics is at a point where it's accelerated, lots of things are happening, and that is, I think, very exciting for all of us that care about robotics to be in it, because I think lots of things are happening, and while it can feel overwhelming sometimes, it's actually, I think, very promising. I think that's how you actually manage to bring the field forward. So maybe very quickly from me, I think some of the things that I wanted to talk or discuss with you have been that we have capable models, the Gemini, ChatGPT, that we can build on top. We can show generalization, we can show transfer between robots, and we have also seen how RL can give us some tools to go beyond the classic method of teleoperation for collecting data at scale. What I haven't covered, but it's also very important, is that hands. How do you do very high dexterity manipulation with hands? We have touched that 3-finger robots, a human that was kind of almost doing grasping. So there's lots of work that still needs to happen in hands. RL for VLAs. This is done already in Gemini, in ChatGPT, but we don't have yet a recipe that works in Google. Outside, definitely, there's lots of people doing very nice work around it. High dexterity, tactile and force are extremely important. There was no tactile and no force in these projects. We are looking at it, but I would say there is not yet a recipe that is yet, oh, if you use tactile of this type and you put in the model, it's definitely going to help you. We have tried, and we keep on seeing that the better your model, the more things it can do just with vision, which has been extremely surprising. But at the same time, they just test that because we're only using teleoperation doesn't have haptics, we cannot solve those, even at the stage of collecting data. So we're finding these problems. We already talked about simulation, human data, world models, so everyone already asked about this. That's very great. Human-robot interaction, like the human now needs to interact with a person, that's a completely big, enormous field that we are not touching yet. Whole body control, we have seen lots of examples. That's something that we haven't covered today. And I wanted to just give you some advice. Take it if you want. The first one I think is the most important one. And it might come a bit surprising, but I think that is the time to be an early adopter. I think you might have used Gemini, ChatGPT, Claude. I would say use it a lot. For your work, for your research, don't use it blindly. That's the worst you can do. But if it can really help you, like if you come to Deepmind, everyone is crazy about these tools. Really crazy. Especially coding agents, they do marvels. So I would really encourage you to try some of this, because it really speeds up, it really makes your work. We're all very productive right now thanks to those. And basically we're running workshops to get everyone at the company to use them, because it doesn't make any sense to have someone that doesn't use those. So if we can get everyone to use them, we're really pushing for that. So that's, I think, to convey how important this is. If you're going to work on research at a company, think about the scaling. I think scaling is very important. We used to work with our own problems and our own questions. And now we're at the point where we want to work with companies and partners to tell us, I want you to solve this task. Because once the problem doesn't come from you, it comes from someone else. If you're making progress, it's true progress. So finding solutions at a scale and problems that make sense to answer, for us is very important to push robotics forward. And finally, for those of you that want to go into PhD, that are already in PhD or postdoc, the best research is what matters. Like when you talk to a candidate and you ask, okay, what have you been doing? You usually ask about that paper that you think is the most important one. The work that they are really probably more proud of, that they really think is really pushing the field forward. The sour thing is that there is a lot of noise. There is lots of papers. We are all missing papers. And it's good for you to remind this and advocate for yourself. It's not the answer that we want to give, but unfortunately we're not in a place where there is only 100 people in robotics. There is tens of thousands, if not more. So you need to be mindful about this. I don't think there is a recipe. When I was doing my work, it was not as extreme as it is right now, but I think it's something to remember. You don't want to do lots of work, but the one that you do, just go to conferences, go to workshops, try to present it, try to talk to people about it. That's useful. And with that, if you still have any questions, I'm very happy to take them.